this number is like 2.10 times 10 to the 5th plus 3.73 times 10 to the 4th plus 2.423 times 10 to the, who cares, 6, whatever. So the way I do these, because you know when you add, you round to what? When you add sig figs?
The last, at least decimal place.
Decimal places, right? So I look at this number. That number has no decimal places. It doesn't, right?
Yeah.
Right, it doesn't. It's 21,000, whatever, 210,000, whatever, right? So this has no decimal places. This has no decimal places. And this one has no decimal places. So when I taught the kid, I'm like, put in your calculator and then rewrite the number with no decimal places, right? So the kid comes back, failed for quiz, failed. Like everything marked wrong, right? So she pulls out the quiz and I'm like, all of these are right. And so this teacher gave her a little handout and told her to study it because she really needs to learn how to do this appropriately. And so what the teacher was doing was saying, this is a 2 decimal place number. This is a 3 decimal. That's not decimal places. There are no decimal places in the number. Anyway, it's just really sad. It's really sad. So I wrote a letter back to the ACL lady who sent it to the teacher, and I was like giving her a practical example. If we have a balance, and the balance weighs that many grams, right? That's an accuracy of plus or minus 0.01 grams. This is what decimal place significance is about, right? So according to her theory, if we change this grams to a scientific notation gram, which would be what, to the 4th? We've now made our balance really, really accurate. Like, this is like a $5,000 balance. This is like a $200 balance. So, just because we write the number differently, she says the decimal significance is different by doing this. Anyway, so this kid failed a quiz because she did it right. And the teacher responded, and that's why I was like, oh my God, I just read a response to ACL. Well, I understand the situation, but there are many ways to solve these problems. So if Skylar prefers another, that's fine. That was her response. I don't know. So what the ACL lady's saying, if this particular quiz grade affects her final grade to the point where to take it up with their supervisor. So I might end up having to go and actually teach something there because they don't know how to do this. Anyway, I'm just flabbergasted. This is a private school. How much are those parents paying to send their kids there? To be taught wrong. Out of control. Crazy. Crazy. Crazy stuff. Guys are getting a good free public education. I mean, you have activity fees, but there's activity fees everywhere.
Yeah.
Yeah, but there's people that go and live in the trailer parks and the apartments all around here so they can send people here. All right, so what we are looking at is replacing hydrogens on these chair conformations and realizing that when we do a chair flip now, we're not necessarily going to have 2 things of equal energy. And this is going to tie into the concept of cis and trans. What we need to look at when we're deciding if prior to a ring flip something is more or less stable than after a ring flip, what we're looking at is that diaxial interaction. Does anyone have a cyclobuilt? If you don't, that's fine. I'm just trying to do visual. So imagine in your head the chair, right? You have all those axial hydrogens going up, okay? The axial hydrogens, those are experiencing diaxial interaction. So if we replace those axial hydrogens with bigger groups like methyls and ethyls and isopropyls, the diaxial interaction increases. And that causes really, really unstable rings. So not unstable, just higher energy rings. So when you flip and something goes to equatorial, there is no diaxial interaction when big groups are equatorial. So that's kind of the goal. To lower energy, we want our bigger groups equatorial. Okay? grade the kids' papers, send it back to the teacher and say, this is what her grade should be. And she'll probably just change it. Sorry, it's on my brain. I'm just flabbergasted. Flabbergasted.
But you know, back makes it seem like she doesn't realize how long it is.
If I did something like that, it would be really hard, but I'd be like, holy crap, yeah, I never saw it that way. I'm wrong. And I would go to the kid and say, I'm really sorry. I'd go to all my kids. I'd be like, yeah, I taught this wrong. So everyone, we're gonna throw that quiz away and either retake it or, and the thing is, that type of sig figs, the addition with exponents and scientific notation, you don't use at all. How many times have you done addition of sig figs with scientific notation in AP chemistry? So why is a 15-year-old girl who struggles in math having to do that for chemistry? It's unnecessary. She just needs to throw that whole thing out. Anyway. Okay, so when the groups, like I said, are in the equatorial position, we don't have any diaxial interaction. So don't worry about building it. We're just going to look at the chairs. I want you to actually get you, okay, if you want to build it, you can. I just want you to start with seeing the chairs and how they work. So today, we're going to learn about cis-trans isomers. Cis-trans isomers are actually a type of stereoisomer. A stereoisomer is different than a normal isomer in that the compounds, they have the same molecular formula and the same connectivity. What's different about them is that a group might be axial versus equatorial. That's not really a connectivity difference. They're still the same types of groups on every carbon. It's just an orientation issue. So one type of stereoisomer is a cis-trans isomer. We're going to look at RNS isomers. We're going to look at, what other kinds of isomers? That's the only one I can think of right now. We're going to look at multiple different kinds of stereoisomers, and this is just the first we're seeing. So cis-trans is a subset of stereo. So cis-trans isomers occur when you're locked in a ring, or they occur when you're looking at groups opposite on a double or triple bond. Across the bond. Y'all should move up with all these empty chairs. Like the poor girls in the back are like, and I'm like, there's chairs like right in front of you. You're sitting in. Okay, do we have any questions so far? I know we never looked at them yet, but. So, this is just the breakdown of what we've learned so far. We know isomers, compounds with the same molecular formula. Constitutional, or what was the other one? Structural. Different compounds with the same molecular formula, but the connectivity is different. Here, same connectivity, but there's something about the orientation in space that's different. All right, so these are different representations, and I want you to be able to do them all. This is just demoism. I call this a planar representation, and I call this the wedge representation. When you have a planar representation, this is 1,2-dimethylcyclopentane. You have a planar, you draw your cyclone or whatever, and then you draw these lines on all the vertices, and it actually represents an above or the below the plane. So anything above or below can be seen very clearly. This is not axial and equatorial. Okay, that's not what this translates to. This is just translating to above or below the plane. So, looking at this, do you see how both of these methyls are below the plane? They're both on the same side. They're sisters. They're close to each other. This is a cis version. These are opposite. One's above the plane, one's below the plane, so that is a trans. Because they're locked in this configuration, that's what makes it isomers. If this weren't a ring and these were just single bonds, we'd have rotation. And what would it be called if it rotates differently? It wouldn't be called isomers, they'd be called conformations. Correct. Now the wedge version doesn't really tell you above or below the plane. The wedge version literally tells you, say if this planar were like this, what the broken wedges tell you is that the groups are going back. So remember, around each of these carbons, there's a tetrahedral situation. So if we've got bonds going this way, we've got a pair of bonds going like this. So the carbon is going back and the hydrogen is up front. Here, carbon's going back, hydrogen's coming out here. If the wedge is solid, it means the methyl group is coming out and the hydrogen is in back. So this is more of a front-back thing than an above or below thing. So see, both of these are back, so that's cis. One is back and one is front, and so it's trans. How else could I draw cis? Yeah, both of them solid. So when you're drawing, I mean, give yourself a minute to practice some of this. When you're drawing your wedges, solids to me are really easy to draw. I tend to lean more toward the solids, but I usually draw wedges. I draw my longest line and my smallest, and I just kind of try to increase. Like, yeah, that looks horrible, but yeah. All right, and then again, when you're drawing these, you want to draw the line all the way through and include both groups, even if it's a hydrogen. Because if you don't put anything on it, according to line structure, that means there's a carbon there, right? So we got to start including all our groups when we're doing some of those things. All right. So here is 1,4. And again, you can see that above, below, this is trans, front, back. What is this? Trans. And then this is below, below, or above, front, front, or back, back, below, below, they're cis. So you all see those. Okay. Now, one thing we can't tell, what does this not tell you that chair conformation? Because this is a cyclohexane. What does this not tell you that a chair would tell us? Axial equatorial, which now that we know when you have other groups like that, that we have a stability issue, if we want to know which conformation is more stable, we'd actually have to draw a chair diagram. And so what we're going to start doing now is translating between chairs and planar. Make sure you know how to do that. So this here shows you the chair conformation of 1,4-dimethylcyclohexane. So if we're going to be trans, and they're just arbitrarily starting, they just said, okay, this is carbon 1, 2, 3, yeah. This is carbon 1 and this is 4. I'm going to decide to put the methyl above the plane on 1. So to be trans, it has to be below the plane on 4. This is axial, axial. When I do a ring flip, I get equatorial, equatorial. Due to the fact that we have the existence of what here? What makes it less stable? Yeah, that diaxial interaction makes this one less stable than that one. But we don't know that level of detail unless we have these chair conformations. Please don't memorize that trans is always more stable or less stable, because it depends on what carbons you're at. Like if I were here and I had a trans, where would my trans be? To be above, no, to be below on this one, it would be equatorial, right? So that changes the comparison entirely. So you got to look at each case individually, depending on what carbon your groups are on. So this is the trans 1,4-dimethylcyclohexane. This is cis 1,4. Well, to be cis, if we're going to be below the plane on carbon 1 and below the plane on carbon 4, sorry, and we do a ring flip, do you see how we have an axial and an equatorial in each case? So they're of equal stability. So when I give you a problem like that, you're literally just going to have to draw it. I'll say which is more stable and why.